Picking up section 2.1 with these functions. This asks us how to determine if an equation is a function. First thing I want to talk about is all linear equations that are non-vertical are functions. Okay. Obviously, if they're vertical, they fail the vertical line test. But if they're non-vertical, they're going to be functions. So if there's anything in here that's linear, right here, linear, this thing's a function. Spell it. Okay. Every single x value has one and only one y value. Anything that's polynomial is going to be a function. This here is polynomial, going to be a function. Okay. But I stated that every x value has one and only one y value. So the argument of how do I really determine this is if I plug an x value in, is there any way that I could get two different y values back? Okay, so let's say x here is 2. If I plug x in to be 2, is there any way that I can get a different number for y? Plug x to be 2, I get 4, right? Okay, so I get y equals 2 squared, which is 4. Is there any other way that when I plug 2 in, I get another number other than 4? And there's not. Okay, so this has got to be a function. One way I like to think about it, if I'm not even doing substitution like this, is can I algebraically write y as two different equations here, two different representations of with using x, and I can't. An alternative way is, look at the graph. That's x squared. Does it pass the vertical line test? Absolutely it does. Okay. Look at y squared equals x. Now I know maybe you haven't spent a whole lot of time with y squared equals x. You should have a little bit last year when we talked about conic sections, but y squared equals x is a parabola that opens up that way. This fails the vertical line test. So this thing is not a function. That's one way of thinking about it. Think about plugging an x in. If I go y squared is equal to, let's let x be 2. So I said that. Can you make the argument then, when I solve for y, that it's plus or minus root 2? So when I say x is 2, some of you would look at radical 2 as a y value that goes with it. If I say x is 2, some would look at negative radical 2. I like to think about it this way algebraically. If I solve for y, I get plus or minus root x. Well, that's y equals root x, or y equals negative root x. You have two different rules to solve for y, and that tells me it's not a function. Kind of same analysis here on this third one. Absolute value of y equals x. Okay, absolute value of x equals y. So if I had like y equals this, that is that shape there, and it's going to be a vertical, or it's going to pass the vertical line test. But you notice it's not the x that's absolute value here, it's y. That's going to be what that function looks like. Fails the vertical line test, so not a function. That's the graphical approach. Think about what we've learned. If I have a function in the absolute value, then I know f of x is equal to c, or f of x is equal to the opposite of c, right? Well, what if y, I should say equal c here, if y equals x, then this should say y equals x, or y equals negative x. You have two rules now for y. So if I tell you x is 2, okay, if x is 2, then here y is 2. Okay, so I have the point 2, 2. Here, if I tell you x is 2, plug it in here, it would turn into negative 2. Okay, so x was 2, y would then be negative 2. You have one x value paired with two different y values, and that violates the definition of a function. So those are some strategies for how we can define or determine whether an equation is a function or not. Obviously, the easiest thing to do, especially if you have Desmos, because Desmos is what we call an implicit grapher. For instance, the GeoGebra is the same way. Let's see here. So what I mean by it being an implicit graph,
All right, sorry about that. My microphone died. So when we come back to this, so it's an implicit graph because I can go y squared equals x. So just type it in that way, and it automatically graphs it. Okay. If I was on my TI 384, the y value is already isolated, so I cannot type it in one line and it give me the graph. I have to type it in as like y equals root x and y equals negative root x to actually get it to show this graph. But an implicit grapher basically means that I don't have to isolate y for my program to graph my function. Okay, I can even have it look like this. Okay, we have y's on this, y and x on the same side, and it still graphs it. So that's an implicit grapher, contrary to what you would see on a TI 384. That's maybe the easiest way to determine if something's a function. Graph it and then run it through the vertical line test. Now, if you don't have the graphing capacity, then this algebraic understanding is then your go-to. All right, so the next thing we'll talk about is the domain and range, and how we find the domain and range, and how we express it then in interval notation. Okay, couple of vocabulary words here real quick. Independent variable. Okay, it is the variable that can take on any value and it does not rely on another value. Okay, well, if you think about that in regards to our two-dimensional plane, our xy axes or Cartesian plane, that is your input, which is your x values, which we rename as our domain. Okay, that then gives us our dependent variable, being the other component. That is your output. Our output in functions is dependent on what we put in. This is obviously your y values, and we cluster those together as what we call the range. Now, the way I remember this, because people get these confused, x alphabetically comes before y. Domain alphabetically comes before range. And then you can say, okay, well, x and d, x and domain match up, y and range match up. Okay. One thing you gotta know is that when I'm doing domain, I'm reading my graph from left to right. So I'm gonna go through and do this one with domain. So what you're gonna do, essentially all that happens is that you take, much like we did with the vertical line test, or even with the when we were working with interval notation in the inequalities, you're going to take your vertical line for the domain and you're going to start tracing it through until you intersect a defined value on your graph. So right there, at an x value of 2, I would have an ordered pair right there. Okay, so I'm going to identify my first x value, 2. Okay, now it's an open dot, so it's really not 2, it's the immediate value to the right of 2. And then I'm going to start scrolling this line through, and it's intersecting all these. So I don't want to write down that 2 is an x value, and then 2.1 is an x value, and 2.01, and 2.5 and 3. I want to write the first one down, and then where is the last one? Where is the last x value? It's at 8. Now, because it's a closed dot, we put a bracket around it. So basically what we're saying is This is my domain, so we usually put a capital D and then a semicolon, or I guess colon, out in front. So the domain is 2 to 8, not including 2, including 8. Basically what it says is if you were to write all the ordered pairs for this segment, your X values are only going to be numbers that come from that interval. We do the same thing with range. Now range is a little bit different though, and this is the one that usually people struggle with. And this is key. You hear me say this a lot. Range, you start at the bottom of your graph. Okay, because it's got this has to be chronological. So our smaller numbers come lower on the graph. So what you're going to do is you're going to take this horizontal line and you're going to start moving it up and see what is the first Y value we intersect. The first Y value that we would see moving bottom up is 6. And because there's a solid dot there, we're going to put a bracket there. And we're going to take that blue line and keep traveling up through my graph until I reach the last value that my graph, that line passes through on my graph. And it's at 8. But it's really not 8. The last Y value would be 7.9 repeating forever. Just because there's an open dot there. So we put a parenthesis. So no matter what, if you were to pick off any ordered pair, let's say that point right there, it's going to have an X value that comes out of that red set of numbers, and it's going to have a Y value that comes out of that blue set of numbers. And that's how we identify our domain and range in interval notation. Same thing happens over here on this one. So let's take this line. Okay, do the domain. What's the first X value I come across? Be -5. Keep traveling that thing through. The last X value you come across would be 3. And it's an open dot at 3. The only thing you gotta pay attention to, I mean, there could be breaks in here. You can see in some of these other examples, there are breaks. There could be holes. We just gotta pay attention to any potential situation that might have this vertical line not passing through a point on my curve. So that's my domain. Now I'm going to do the same thing for range, but we're going to take horizontal line. Let me be easier to do it this way. Take that horizontal line, and we're going to pass that through. So what's the first? I'm moving it from the bottom up. The first Y value you come in contact with. So right here where my cursor is, that's the first point that red line touches my graph. What would be the Y value of that? Well, it's on the x-axis, so that Y value is 0. Now I'm going to continue to pull that thing up, and I'm going to keep intersecting. I'm going to intersect values at 1/2, 3/4, so 1, 1.25, 1.5. I get up to 2, and now my argument is, will there be a 2? There's a closed dot here, and there's an open dot there. But the question is, what am I doing here? What am I writing? I'm writing all the Y values that could potentially be written from these ordered pairs. Well, that ordered pair is definitely -5, 2. So 2 should be a Y value that shows up. So I can include 2, even though over here it's excluded. Remember, the idea here is that all these R values, range values, are the Y values that could show up if I listed the infinite number of ordered pairs here on this curve and looked at all the Y values. They are going to be of that set. This one here, domain, same concept. What is the first X value that I'm coming in contact here with? Scrolling through, first X value, -4. And now, keep going. What's the last X value? What's that arrow tell me? The arrow tells me it goes on forever. So we're going out to infinity. Range. Okay, so here we're using the horizontal bar. Moving from bottom up, first Y value I come in contact with, -2. Okay. Now, as I move this up, okay, obviously I stop intersecting there, but think about what this arrow means. This arrow means that that graph's going to keep doing what it's doing, and there will be a point right there that horizontal line intersects. Okay, so that arrow is telling me not only is it moving in the x direction forever, it is growing in the y direction forever. Now it's going to take a long time to get to like 1,000 in the y direction, but it'll get there. I just might have to be out at 100 billion for the x value to get there, but it'll get there. So we're going to positive infinity as well in the range. This one here, let's see here. Do I have? Yeah, it looks like those are dots there. So this graph here would come from a rational function. Let's talk about our domain first. Okay, so as I take this and traverse it through, first x value I come across would be -6. It's a solid dot, so I'll include it. And now I keep going, and I intersect, and right there, okay, is the last place that I'm intersecting this blue curve. And you see it's telling me what that x value is. It's saying that position where that red line is on my x-axis at -1/6. And we're going to be inclusive. Okay. Now, as I take that red line and pass it through like this little region right here, don't come in contact with anything. There are no values that are defined there. But my domain picks up again when I get to 1/6 because now I'm intersecting this point up here. So I'm going to continue my domain now at 1/6. And I keep passing that thing through. It'll eventually be the last x value at 6. And if you remember, when we have multiple intervals, we have to union those. Range is the same concept, but moving from bottom up now and dealing with the y values. So what's the first y value I come in contact with? -6. I'm going to move up. What's the last y value I come in contact with? This little branch here. Last y value will be -1/6. I'm going to skip some values in here because they're not defined, but right there where my cursor is, first x value, or sorry, first y value would be this 1/6, positive 1/6. And then when I keep moving that thing up to 6, will be the last one. So this is kind of a unique one where the domain and the range are identical. We can look at something like this. Let's say 1, 2, 3, 1, 2, 3. Let's say that I have a graph that starts right here, and then it goes up. Let's put an open dot there, and let's say it comes back down. And let's put an open dot there, and then let's just jump solid dot to there. Okay, so if I asked you what is the domain of this thing? Okay, so if I think about my vertical line here and I start passing it through, first x value I come in contact with would be -3. And that was a terrible choice of a line. But as I move that through, so -3, I come into an issue right here. We'll say it's -1. There's an open dot there. So this graph is not defined for -1, meaning if I were to go list all the ordered pairs on here, -1 is not going to show up as an x value because it's an open dot. Now negative 1.000001 will show up, and negative 0.999999 will show up as x values in order pairs, but negative 1 will not. How do I express all those other ones? I use negative 1 in my interval, but I put a parenthesis around it to tell everybody, from the left-hand side, you're not getting the negative 1. You're not getting there. You can get to negative 1.00000001, but you can't use negative 1. Now, as I move that let's go back to this. Alright, so as I move this line through here then, once I skip over negative 1, I'm back into finding x values or having defined x values. So just to the right of negative 1, we should have our next x value. And I'll take that line, I'll keep scrolling through, and I get up to 2. Now it's an open dot at 2, so I don't include 2. Okay. Now if I look at this, I'm going to union those. Okay, so far, if you think about this, we've gone from negative 3 all the way up to 2. Started at negative 3 all the way up to 2. And we talked about last week, when I have that right there, when I have a number union, the same number, in parentheses around that number, that is our convention for kicking that value, that x value, out of that set of values, that interval. Now as I continue here, I'm going to skip over these values here. They don't belong. There's no x value for this graph of like 2.5. My next x value I come in contact with is 3. So I'm going to make another interval here of 3. I'm going to include it because it's solid. And now if I think about this red line going all the way through, this arrow tells us you never stop. It's going to keep going to infinity. And we union that with the rest. So there's my domain. Okay. Now my range, same type of structure, same type of procedure. But now we're just going to start at the bottom and move our way up. So I'm starting at the bottom. What's the first y value I come in contact with? Right here. Now remember, this is open, but that one's closed. So if we were to write all the ordered pairs, will there be an ordered pair with a y value of negative 1? That one will not. So negative 1 needs to be included because there will be an ordered pair with that y value. Okay, now I keep going, and this is where it gets kind of tricky. Because a lot of people are going to say, well, your range stops at 3 because there's an open dot there. But what's this arrow tell me? This arrow tells me that these are going to go on forever in that direction. So is 3 my last value? Or is 4? Or is 5? Or do we see that my range goes from negative 1 all the way up to infinity? Because that's what that arrow is telling me. That thing's going to go on and keep growing in the y direction up to infinity. So that's how we kind of talk about domain range with graphs. We'll do a lot of that. A lot more practice of that. When we do this algebraically, okay, finding domains for an equation algebraically, there's 2 issues that we have. Number 1 issue, division by 0. Okay, so if there is a potential for division by 0, you need to make sure that that is kicked out of your domain. Domains are essentially what value can I use as input to where I will get a defined output. Okay, so division by 0, like if I'm right here, if I put negative 3 in, I'm going to get 1 over 3 minus 3, which gives me 1 over 0, and that's not a defined output. That's not a numerical value. I don't know what that is. It's undefined. So negative 3 would be a domain issue for me. Okay, so division by 0 is a problem, and then even roots. Okay, so even a couple different ways you might see this expressed. Even roots, square root, fourth root, sixth root. Sometimes they'll express it where nth root, where n is positive. I won't say positive, I won't say even. N is even and positive. Or you might see it where they say like 2n, and we'll say where n is a natural number. Because think if n is a natural number, if the first natural number is 1, so that'd be 2 there, it'd be square root. If it was 2, it'd be 2 times 2, fourth root. If it was 3, it'd be sixth root. So this here is an effective way of saying all of those. But you can't take even roots of negative numbers. So that would be an issue here. So going through these examples, example 1 says, how do I determine what the domain is of this? Well, I'm not allowed, this number cannot be negative. So the way we do this with square roots or fourth roots or sixth roots is you take the radicand and you say that it has to be positive or 0. Okay, so x plus 1 has to be greater or equal to 0, and I solve that. X has to be greater than or equal to -1. That's the set builder notation. Okay, usually if it's set builder, you would maybe see it a little bit more explicit that way. But we're going to want domain and range identified in interval notation. So I'm going to say domain x values that are bigger than or equal to -1 means they start at -1 and they go to infinity. That's my domain. Those are the only values I can plug in here and get a valid output. If I do example 2, okay, example 2 basically says I cannot divide by 0. So when you have division, essentially what you're going to do is you're going to say 3 plus x cannot equal 0. And when you have an equation with does not equal, you still treat it the same way, like it was an equal sign. Just solve for x. So x cannot be -3. Okay, so a lot of times we would say, set builder notation would be x such that x cannot be 3. Sometimes you would write like, sometimes you might see it written this way, x such that x is an element of all real numbers. And they'll put like a semicolon, x cannot be -3. But in interval notation, all we've got to do is say, okay, well, we go from -infinity up to -3, union -3 up to infinity. And when we think about it, it goes from -infinity to positive infinity. And we have that structure that we talked about earlier, right? Where we talk about it? Right here, where we kicked out that -1 in that problem. Here, the number we got kicked out of that we're not allowed to have is -3, so that's how we effectively remove that from our list of values from -infinity to positive infinity. This one, do we have division by 0? And do we have even roots? The answer to both of those is no. So this here, the domain, is all real numbers. Nothing gets removed. Nothing gets kicked out. If I want to write it in interval notation, that's all real numbers in interval notation. Example 4, a couple things going on here in example 4. We have division by 0, so x minus 5 cannot be 0. And, okay, because both of these have to be satisfied. It has to be an and statement here. You can't maybe have a number up here that gives me an output, but that same number down here does not give me an output. Okay, so both the numerator and denominator need to be defined at the same time to get a quotient. So we have x minus 5 cannot be 0, and x minus 3 has to be greater or equal to 0. So x cannot be 5, and x has to be greater or equal to 3. Well, if you think about that graphically, and I think sometimes with these, when you have division and roots at the same time, maybe a graph makes sense. So put in 3, x has to be greater than or equal to 3. But this, and it says and, so I need this incorporated. X cannot be 5. There's 4, there's 5. Okay, so we're going to open dot there. So how do I show that? How do I demonstrate this solution in interval notation? I go 3 to 5. I'm going to jump over 5 and kick it out, and then go to infinity. And basically what that says is, okay, so I can choose 3, because if I put 3 in, it gives me square root of 0 over negative 2. Well, that's just 0. I can do that, get an output. Okay, can I put 5 in? Because 5 works up top. 5 minus 3 is root 2. 5 on the bottom gives me 0. That's undefined. Even though it worked up top, it did not work on the bottom for me. It gave me division by 0, and that's an undefined quantity. So that's why 5 had to get kicked out. Any other number is going to give me a value up top and a value on the bottom that I can do division with, so that's why nothing else gets removed. Example 5. The only thing we got to worry about here now, okay, so we have division and we have roots, and that this is a special case because the root is the divisor. Okay, so because of this, so that root, that 2x plus 1, by being a root, has to be greater than or equal to 0. Okay, because we can take square root of numbers. We can take square root of 0, is what I meant to say. So we can have 2x plus 1 is greater or equal to 0. But because this root is in the denominator, you cannot have the equality aspect. So in this case, we just want to say 2x plus 1 is greater than 0. I'll explain in more detail when we're done. We have an answer here why that makes sense. But if I have 2x is greater than negative 1 now, x has got to be greater than negative 1/2. Well, x is greater than negative 1/2. In interval notation would look like that. Obviously, if I'm graphing this, let's say negative 1/2 is there, it would be that stuff to the right, which is what this is showing in interval notation. Now, why couldn't I use negative 1/2? Because I get 1 up top. If I put negative 1/2 in, I get square root of 0. Well, we know we can take square root of 0. I get 0. But what's 1 divided by 0? It's undefined. That's why we could not have that equality inside that algebraic statement. We'll stop there. Piecewise functions are on deck. Those are going to be probably something you guys haven't seen or dealt with too much. We'll spend quite a bit of time on those. If you guys get any questions, please don't hesitate to reach out. This stuff is very important. Domains and ranges are going to be something that's going to be stuck around for the rest of the year, and pretty much the rest of your mathematics careers. No matter how far you go, you're going to be talking about domains and ranges all the time.